My partner Carly and I built a tower made from straws and masking tape to withstand added weight on an earthquake simulation. Before we started to construct our stable towers to withstand an earthquake simulation, we had to make a design and plan the dimensions of our tower. The tower had a minimum height of 36 centimeters without the unique roof we had to later add, and have 2 floors to hold sandbags. The base of our tower is very important, and the building inspectors required the tower to be bolted into the cardboard base. We did this by drilling 4 holes in the cardboard, putting straws through them, bending the straws, and taping them down. To strengthen our tower, my partner and I doubled up straws for support when we were just starting with the framing of our tower. When the frame had been placed, it was important for me to check that the amount of tape we placed could securely hold our straws together. Finally, after a few weeks of planning and construction, we had finished our tower, as epic and sturdy as it will ever be. My partner and I added a unique Japanese-style roof with 2 Japanese flags, a Yu-Gi-Oh drawing, and a demented Caillou drawing. With the new building codes in place, our design changed. Our tower is now 63.5 centimeters long in total, 25 centimeters on the first floor, 27 on the second floor, and the width is 21 centimeters. To strengthen our tower, we added cross supports between framing in the shape of an X. Then we put a pillar in between the roof and the second floor, and the first and second floor, and the first floor and the basement. My partner and I wrapped tape in between angles of the cross supports in the framing. Finally, we bolted straws into our cardboard base. I tested the tower to see if it could even hold 4 sandbags without the shaking. This process was called static testing. The result of the testing was that our tower could comfortably hold 4 sandbags with no signs of supports bending or too much tension. Of all the features of our tower, I'd say the strongest one is the doubled up supports. To get a preferable height, we used 2 sets of 1.5 straws, 25 centimeters, to create a support for each floor. In total, my partner and I manufactured 16 1.5 straws, doubled them up, and put 4 on the basement and first floor. In my opinion, the pillars in the middle are probably the weakest parts of our tower, because unlike an X shape and doubled up straws that don't bend easily, the pillar in the middle is thin and will bend easily. The weak supports could cause the tower to collapse on itself. By far, tape was the most important component of our tower. My partner and I used tape of different thickness and lengths for different parts of our tower. For example, to secure the base of our tower, my partner and I used thicker and shorter tape, and for securing supports together, we used thinner and longer tape. The technique we used was sticking tape on the inside of the corners and wrapping it around 2 perpendicular straws. When the building inspectors required a unique roof towards the end of the build, we were given 15 additional straws, and the unlimited supply of tape was refilled. We decided to do a Japanese-style roof. We had to be cautious about cutting and taping straws with the limited amount we got for the roof. So we decided to do some quick calculations for the number of straws our roof would use and set to work. We started by adding 2 sandbags to our tower and shaking it. Then, each round we added 2 more. Our tower made it to 14 sandbags on the 7th round of shaking and collapsed pretty early into the 10 seconds. During the earthquake shaking, our tower's movement was recorded by a sensor in the tower. The sensor plotted the data from the earthquake simulation on an XYZ graph. On the graph, the X represents the side-to-side motion of our tower. This movement is very predictable, and it spiked, fell, and spiked again. The Y-axis represents the forward and back motion of our tower. On the graph, the motion is shown as a small rapid rise and fall on the graph. The Z-axis represents the up and down motion of our tower. Our building was pulled from its foundation bolts during the shaking. The Z-axis would rise, buffer, fall, and buffer. The graph is a great way of showing the movement of our tower during the shaking. Our tower supported 14 sandbags, and it failed at the center upright piece, where it bent very early into the shaking. To strengthen our tower, we could have doubled up the center upright piece to keep it from bending. I learned that each piece is important in the tower, and you have to find the strong and weak parts. I enjoyed building the unique roof, doing the testing, and working with my partner Carl. Drop the mic.
And when this failed, the whole thing collapsed. Next time, if we did this again.
Our building supported 14 sandbags. It failed at the center support piece here. To improve our building, we could have added more tape and more center support. I learned that it takes a lot of hard work, determination, and friendship to build an earthquake-proof building. I enjoyed working with my partner, JJ Goody.
Drop the mic.